Okay, good afternoon, everyone. Good afternoon. Those students who have joined us this week, in the second week, I'll repeat some information for you regarding the module and all the resources where you can find them. Okay, so I'll go through those so you can access them. First important thing, the platform that you should know about is My Times. On My Times, you will find all the resources, study resources, and all the information related to your assessments, and any other notifications, announcements, you will find them over there. And I'll quickly go through the main sections for this module on My Times. In your announcement sections, if there is any replacement class or any other announcement, you will I'll post it over there, and your lecturers will also, your tutor, those who will be teaching you tutorials, they will post the information or the announcement over there, and you should be able to receive an email or a notification about that. And after that, you have your module information section. There you can find module information document where most important things are your MLOs, and there are 3 MLOs. One is mapped against your test. It will be in week 9. Assessment details can also be found over there. When will we conduct your assessments? Test will be in week 9. You can find that in module information document, and your group assignment also, and then your final exam. Okay, and which topics we will cover each week, you can find all that information in your MI, module information document, that you can find on My Times under module information section. Okay, please no talking. Then next section is your reference books. There are 5 reference books. One of them is the main one. Most of the information that will be included in your lectures will be taken from the first book. This you can either get from this on-campus library, or you can log in to the library portal, online library portal, using your student email address and password. So you can access the book from there. If you don't find it, let me know. And there are 4 additional study resources for your self-study. Okay, all the information about that is included in the reference books section. Then your lecture notes, all the weekly lecture notes will be posted here. Then tutorial exercises, that you will have 2 classes per week for this module. One will be your lecture class, that is today, and one will be your tutorial class that you need to check. There are 20 tutorial sections. You need to check in your timetable which section you belong to, and go to the correct one. Okay. After that, all the information related to test, it carries 30% weightage out of the total 100%. All the information, all the topics that will be included, it will be posted in this section. And then your group assignment details, they will be posted in the last section, which you can find, that also carries 30% weightage. Okay. So this is about the My Times. And main mode of communication will be MS Teams. If you log into your student email, there on the top left corner, you can access Teams through that. Okay, you will be able to find your group for lecture session, for tutorial session over there, and also you can individually communicate with me if you have any queries. Okay, so main mode of communication will be MS Teams. All right, and other than that, you have your attendance. This I told you in week 1. For those who have joined in week 2, I'll repeat for those. if your attendance will be marked in the last 15 minutes of lecture session and your tutorial session, and once the code is generated, you will be able to mark your attendance through your student app, and you will have 10 minutes to mark your attendance. If you face any issue, please let me know during the class. After the class, I will not accept if you are unable to mark your attendance. Come to me during the class, okay? And that's all. These are the important things that you need to know. In your, let's move to week 1 lecture. Last week, week 1, we covered propositional logic, where we studied about what propositions are and what are compound propositions, how can you form compound propositions, and different cases, special cases of compound propositions, that is tautology and contradiction, and then conditional statements, 3 different variants of conditional statements, and what logical equivalence is, how to find out whether 2 propositions are logically equivalent to each other or not using truth table, how to construct the truth table, and for all logical connectives, the rules, how to construct, and the rules for each for the 5 logical connectives that we covered: negation, conjunction, disjunction, implication, which is the conditional, and biconditional, which is equivalence. And then we were left with one main topic, which is argument, that we will cover today. Okay, so let's start with what argument is. Okay, first of all, let's look at what argument is. Argument is simply a sequence of propositions where you have 2 components. One is premise and second is conclusion. Okay. There can be 2, 3, 4 or more propositions, compound propositions in an argument. The final one, where you have a therefore symbol, that is known as the conclusion. Every statement before that is known as premise. Okay, so that is what an argument is. Let's look at it with an example. Here you see an argument. You have 2 premises, and then the last statement is your final statement called conclusion, and you have a therefore symbol here. And next thing that you should know about argument is how to find whether an argument is valid or invalid. How to find out whether an argument is valid or not, you will construct truth table. So in this lecture, the focus on answering the questions is through construction of truth tables. Please, no talking. No talking, please. Okay. How to find out whether an argument is valid or not, you will construct a truth table again. For most of the questions, all of the questions actually, you will answer them by constructing the truth table. So to find out whether this argument is valid or not, again we will construct a truth table. Let's try. Actually, you have it over here. I have taught you how to, the tips to construct complete neat truth table, which is the first step to draw the truth table is, can anybody tell me from last week? What is the first step that you take to draw the truth table? Yeah, yes. Yeah, see how many unique statements you have, which you can find out by the unique statement variables. So in this argument, is it visible, or should I put it on slideshow? Visible? Okay. So first of all, we need to find out how many unique variables we have. That will tell us how many total rows we will have. So in this argument, we have three statements, so P, Q, and R. So we will have 8 rows, and a tip that I taught you is, for the first variable, write down 4 trues and 4 false. For the second variable, write down 2 trues, 2 false, 2 trues, 2 false, so in pairs, true, false. And for the third variable, just alternate, true, false, true, false, true, false. So 4, 2, and 3, okay? This will help you in constructing your truth table neatly, and also it will make sure that you have complete truth table. You are not missing any row, okay? Or you're not missing any combination of truth values. And next tip is to refer to the hierarchy of logical connectives, which is your parentheses, and then you have negation, then you have conjunction and disjunction, and then implication and equivalence. So if you see any parentheses, write down the truth values for that. Here in this argument, there are no parentheses, so you will move on to the next one. Check if there are any individual statements that are negated. Write down the truth values for that. Here, if you see in all 3 statements that you have in this argument, you have one statement which is negated, so truth values for that. And there is no other statement that is negated, so you move on to the next in the hierarchy, conjunction, disjunction. In all 3 statements, check where you have conjunction and disjunction, write down truth values for that. And after that, lastly, implication or the conditional and equivalence or the biconditional. So you draw your truth table like this, step by step. And the next step is to find out whether an argument is valid or not. There is one rule. You will focus on the column for your first premise, second premise, and conclusion. And you will focus on those rows where both the premises have true as their truth values, means both the premises are true. Against those rows, you will check whether the conclusion is also true or not, okay? So in all those rows where both the premises are true, the conclusion must also be true. So you have 4 such rows where both the premises are true. You will check against those. For the first one, yes, conclusion is true. For the second one, both the premises are true, but the conclusion is false. It makes the argument invalid. It goes against the rule of validity of an argument. So even if you have one case where all the premises are true, but the conclusion is false, that makes the argument invalid, okay? So what is the rule for validity of an argument? It is that in all the cases in the truth table where all the premises are true, conclusion must also be true in those rows, okay, for the argument to be valid. All right? Is it clear? Clear? Okay. So with this, we will move on to the next lecture for modus ponens and modus tollens. We have that in next lecture as well, so we will cover that all together, okay, when we reach that topic in second lecture. So you can access the second lecture through my times. It's about predicates and the logic of quantified statements. If you have any questions about arguments, validity of an argument, you can ask me. Okay, let's start with the second lecture. Predicates and the logic of quantified statements. So there are two parts in this lecture. One is where we will study about what predicates are, how to find out the truth values of a predicate. Can you hear me on that side at the end? Am I audible? If not, you can please come to this side. Okay. All right. So truth values of a predicate, and then how to find out the truth set of a predicate. And next we will cover quantifiers. We will cover two main quantifiers in this lecture: universal quantifier and existential quantifier. Each of them make up universal statements and existential statements each. Okay. And then we will check the truth and falsity of universal statements and existential statements. Then we will have formal versus informal language, similar to what we covered in last lecture. And lastly, we will have in part 1 universal conditional statements. So we will have universal statements, existential statements, and universal conditional statements. In next part, we will cover the negations of all these types of statements. How to negate universal statements, how to negate existential statements, how to negate universal conditional statements. Let's go through the definition first. So a predicate, it's a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. What does it mean? Let me teach you in context of different types of statements that we will cover. In English language, you have subject and predicate. It's similar to that. The predicate part tells you the information about a subject. In logic, in quantified logic, quantified statements, let's look at, let's say, universal statement. I will teach you about what this is later. You will have two parts in the statements that we will study in this lecture. First part on the left hand side will be quantifier, and the part on the right hand side, this will be predicate. Okay, this could be any mathematical expression. It could be a mathematical equation, it could be a mathematical inequality, it could be a statement. Okay, and you will call it as predicate, and it is also known as function. The value here, this is the general form of writing the predicate, and you will, in this type of statement, you will have a domain which could be any set of numbers. It could be a set of real numbers, set of natural numbers, set of integers, positive integers, rational numbers, or any other specific set given to you with finite numbers of values. Okay? And when this statement or this predicate will be true, we will look at it in two contexts. One is universal and one is existential. Let's look at it in the form of, in the context of universal statement first. So your universal statement will be true. This is known as domain generally. Okay, and your universal statement will be true when this predicate holds true for all the values of x from the domain. Okay, from the set of numbers given to you. All right. Okay. This is just one example from universal statements to help you understand what predicate is and what is its role. Okay, and this predicate could also be a conditional that we have covered in last week's lecture, which is in the if and then form. So This predicate could be in the form of a conditional, in the form of a mathematical equation, in the form of a mathematical inequality, or in the form of a statement. And this predicate must hold true for all or certain values of x from the given number, from the given set of numbers. Okay, this is what predicate is. Next, we will look at through an example how to find truth values of a predicate. So we will look at this example. This is also from your book. Okay. So let's say, let P of x be the predicate, x square is greater than x. So I told you your predicate could be an inequality or an expression. So here you have predicate in the form of a mathematical expression with domain, the set R of all real numbers. So you should know, it is prerequisite knowledge, you should know the notations for common set of numbers, like real numbers, you denote it with R, natural numbers with N, integers with Z, positive integers with the positive symbol, and rational numbers with Q. Okay, so let P of x be the predicate x square is greater than x with the domain, the set R of all real numbers. Write P of 2, P of 1 by 2, and P of minus 1 by 2, and indicate which of these statements are true and which are false. Okay, so certain values of x are given to you from the set of real numbers, which is the domain. What you will do is, you will check for all of these. You will simply plug in these values of x in this predicate. And simply that's how you will find out the truth values. Okay, so is this true? Right, it's true. So P of 2, this predicate holds true. How you will read it or how you will mention it? Predicate x square is greater than x holds true for this value of x, for 2. Okay, this is one of the values of x from the set of real numbers. Then you will check for the next value of x from the set of real numbers, which is given to you, 1 by 2. Is it true? It's false. Okay, so the truth value of this predicate is false. So this predicate is false for the given value of x, that is given to you in the question. Next, you will check the last one. Is it true or false? True or false? True. 1 by 4 is greater than minus 1 by 2. Okay, so this is true. So that is simply how you find out the truth values of a given predicate. You check the predicate, you check what values of x are given to you from the domain. Domain is the set of numbers that is given to you. Here it is a set of real numbers, and then simply plug in those values of x in the predicate that is given to you and write down the truth values. Okay, clear? Understand? Yes? No? Okay. Next is how to find out the truth set of a predicate. Okay, let me go through the definition first and then we will understand it through an example. If P of x is a predicate and x has domain D, the truth set of P of x, which is the predicate, is the set of all the elements of the domain that makes P of x true when they are substituted for x. So in the last one, you were checking for certain, like for one by one, you were checking the truth values. Here you will find out all the values of x which makes the predicate true, and you will write those down as the set in the form of a set in these curly brackets. Okay, all the values of x which make the given predicate true. Let's look at it through an example. So let Q of n, this is also, doesn't matter which variable you use. If it is in this form, it means it's a predicate or a function. Same thing, let Q of n be the predicate. Now here, this is the predicate. N is a factor of 8. Find the truth set of Q of n if you are given two questions. If the domain of n is set of positive integers, and second one is the domain of n is set of all integers. So I'll solve the first one for you. From the set of positive integers, you have to find out those values of n which makes this predicate true, so which is n is a factor of 8. So you'll write them down in these curly brackets. Set of positive integers. What is the smallest positive integer that we have? 1. Okay, so set of positive integers, it starts from 1 and up to all the whole numbers. Okay, so all the positive all the values of x from the set of positive integers that are the factors of 8 that you will write down over here. Okay, so what are the factors of 8? Positive factors of 8? Yeah. 2? Yeah. Yeah. Okay. So these are all the all the possible values of n from the set of positive integers that make this predicate true. And this is the truth set of this predicate. Okay. Clear? Is it clear? Okay. Okay, let's solve the next one as well. So now the domain is, what is the domain now in the second one, part B? Yeah, set of all integers. So what will be the truth set then? All the integers mean you will have all the negative numbers included as well. Okay. So what will be the truth set now in part B? Minus 8, minus 4, minus 2, minus 1, and remaining all these, sorry. Okay. So this will be your truth set for part B. Okay. Clear? This is how you find out the truth set for a given predicate. Understand? Clear? Okay. All right. Next topic is quantifiers. Let's look at what quantifiers are. We will cover two main quantifiers here. One is universal. The symbol for that is upside down A. And second one is existential. This is the symbol for that. Let's look at universal quantifier first. I'll go through the definition. Let Q of x be a predicate and D the domain of x. A universal statement is a statement of the form this, for all, how do you read it? For all x, where x belongs to the domain D, such that Q of x or simply Q of x. Okay, this is how you read a statement. This is a universal statement, so this is how you will read. And for this, you can write it or read it in different ways. For all, for every, depending on the context, every, all, any. Okay, so these are all different keywords for reading this universal quantifier. And next what we have, it is defined to be, so now next part will be when a universal statement is true and when it is false. So the rule for the universal statement to be true is that the predicate given to you in the universal statement must hold true for all the values of x from the set of numbers that is given to you from the domain. Okay, like even if one of the values of x make this predicate false, the universal statement is false. You'll say that it's not a universal statement. And that one example, that one value of x from the domain that makes the predicate false, you call it as a counter example. Okay? So the value of x that makes the predicate false, that is called counter example. The rule is, for the truth of universal statement, it should hold true, the predicate should hold true for all the values of x from the domain given to you. Let's look at it through an example again. So this is the question given to you. Now here, a set D is given to you where the values are 1, 2, 3, 4, and 5. And this universal statement you have where the predicate is x square is greater than or equal to x. Now you should know how to write it in how to read it and how to write it in informal form. Okay, how to read it, I have already told you. For all values, or for all x that belong to the domain D where x square is greater than or equal to x. Okay, so how to, let's check whether this universal statement is true or not. How will we check? I have told you about the rule for the truth of universal statement, which is in this in the context of this question, you will check, you will plug in all these values of x, of the x, okay, in this predicate and see whether this predicate holds true or not. Okay, so let's write this. Second value is 2. Now all of these must be true for this universal statement to be true. So is this true? Yes, it's true. Is this true? Oh, sorry. Is this true? 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 This one? Okay. So for all the values of x from the set that is given to you, this predicate holds true. So this universal statement is true. This is a universal statement. Okay? Clear? Let's say, just for the sake of example, let's say you got something like this for this predicate. Let's say, suppose. So is this true? No, right? So what will be this example? Counter example, yes. And you need to find only one counter example to prove that a universal statement doesn't exist or it's false. Okay? You have one more example. Let's solve that also. Now here you have to find out a counter example. Now for all x where x belongs to the set of real numbers, x square is greater than or equal to x, you have to find out a counter example to show that this statement is false. Now set of real numbers, if you know what numbers are included, what this set comprises of, you can choose any value from the set of real numbers to find out the counter example. It's up to you. Okay, as long as it is part of set of real numbers, as long as it is part of the domain that is given to you. Okay, so here in this case the domain is set of real numbers, which we know set of real numbers consists of mostly all of the other common sets, okay, except for some complex numbers. So you can take any value from the set of real numbers that will make this predicate false. Anyone? Yeah. So this is your counter example. Okay. You can choose any. All right. Clear? So what you need to remember is what is the rule for statement, for a universal statement to be false. Okay, that is what you need to know. And also common sets of numbers. Okay. This was the first quantifier and universal statement. So, or also you also call it as universally quantified statement. Next we will look at, is it clear about universal statements? Yes. Yes? Okay. Next we will look at the second quantifier, existential quantifier. This is the symbol for that. I'll go through the definition first. Let Q of X be a predicate and D the domain of X. An existential statement is a statement of the form. How do you read it? There are again different ways. There exists or there exist. Then for some. Okay. Yeah, these are the common ones. For some X or there exists some X which belong to the domain D such that Q of X. Okay, it is defined to be true. So now about the truth and falsity of existential statement. Existential statement is the one where you have existential quantifier. So when an existential statement is true and when it is false, it is defined to be true if and only if Q of X is true for at least one X in D. So it is opposite to the universal statement. For an existential statement to be true, you need to find out only one value of X from the domain which makes this predicate true. Okay, that will make the existential statement true. So in universal, all of them had to be true for the universal statement to be true. In existential, you need to find only one value of X, all right, for the existential statement to be true. Okay, and it will be false only in the case where for all values of X from the given set of numbers, this predicate is false. Okay, in that case, existential statement will be false. Again, let's look at it through an example. So for some m which belong to the set of positive integers such that m square is equal to m, let's see, you need to find only one value from the set of positive integers to make this statement to be true. So from set of positive integers, if you take 1, simple. Okay, so this makes your existential statement true because you have at least one value of X from the set of positive integers for which this given predicate holds true. Okay, let's look at another example. Now here you have to show that this existential statement is false. So remember the rule, existential statement is false when, let's look at it in this in the context of this set, when this predicate is false for all these values of the set given to you. So let's check. So this is false, right? 25 is not equal to 5, right? 36 is not equal to 6, correct? Right? Then 49 is not equal to 7. 64 is not equal to 8. So for all these values of X from this set of numbers given to you, this predicate is false. So this existential statement is false. Okay. So I'll recap for universal statements. When it is true, when for all the values of X from the domain, the predicate holds true. When it is false, when it is when for one value of X from the domain, the predicate is false. That is called as counterexample. This is about universal statement. And then for existential statements, when it is true, when the predicate is true for one value of X from the given set of numbers, which is the domain. And when it is false, when the predicate whole is false for all the values of x given to you from the set of numbers, given to you. Sorry. Okay, clear? Clear? Okay. Any questions? Any questions? Okay. No? No questions? All right, then we will move on to the next topic, which is translating. So you should know, the propositional logic, propositional statements, you should know how to translate the quantified statements from their formal state to informal state, from their informal state to formal state. Okay, so this is your formal universal statement. You have two formal universal statements and one formal existential statement. I told you that you can write these in different ways as long as they are logically correct. So you should know how to read this. This is, one of them is solved over here. So for the first one, let's look at the predicate. X square is greater than or equal to 0. So here also, if you look at predicate, sometimes predicate, about the predicate, you should have some prerequisite knowledge to write down your statements in the informal language. For example, this one, every real number has a non-negative square. So for that, what do I mean by knowing, having the prerequisite knowledge? That square cannot be negative, right? So square of any number, it cannot be negative. Even when you take the square of negative numbers, it results in a positive number, right? So this is what I meant about having the prerequisite knowledge to write down concise universal or existential statements in their informal form. So here, there are different ways of translating from formal to informal. One is every real number, so your domain, every real number has a non-negative square. X square is greater than or equal to 0, which means starting from 1 up to all the positive numbers. Or you can say all real numbers have non-negative squares, or you can say any real number has a non-negative square, or the square of each real number is non-negative. So you can use any of these when you are translating this universal statement from its formal state to informal language. All right? Clear? As long as it is logically correct and as long as you have used the correct keyword for the quantifier. Understand? This one I'll leave for you to solve, to translate. Next, from informal to formal, similar to translation from formal to informal, for the informal, from the informal to formal language also, you should first identify the keywords. Check if you have all, every, any. That will help you in writing down the exact quantifier in the formal form. So all triangles have 3 sides. It means here the keyword is all. It means the quantifier in its formal state will be for all. Cannot see? Oh, frozen. 1 minute. translating from informal to formal, again you have to look for the keywords to write down the correct quantifier. So first example here, all, every, any, whichever it is, and sometimes you might need to read the whole sentence and make sense of the complete sentence. Okay, so let's look at first example. All triangles have 3 sides, so you have the keyword all. The quantifier will be this for all, upside down A. Now you can write it again in the formal form in 2 ways. For a statement to be formal, the minimum that you need to have is the quantifier. Okay, the quantifier, its notation or the symbol, and you can assign, let's say triangle here, you can assign it to a variable. Okay, so you can assign the whatever subject is given to you to any variable. For example, this triangle, you can assign it to the variable t. It means you will have all the triangles present in t, and then you can write down its quantifier part, and you can also write it down completely incomplete, like you will write down in this form. Okay, so this is your complete formal form, but the minimum you can write it down like this, or you can write it down like this. Okay, all right, the minimum that you need to have is the symbol for the quantifier and the variable. So triangle T, and you will look at what predicate you have. You assigned it to a variable. T has 3 sides. Okay, so this is how it's written, and you see it's written in singular form. So we write the predicate in singular form in your quantified statements. Okay, and another way is that this is the one that I told you about. For all t, it's up to you. You can choose any variable that belong to the set of triangles. You can assign it to a bigger set and then write down the predicate. T has 3 sides. Okay, that gives you information about the variable. Okay, is it clear? Understandable? Yes? No? Another example, let me give you this one also. Here, this is what I meant when I said that sometimes you need to look at complete statement to find out what quantifier you will use and how you will convert it from informal to formal language. So here you have an example. This is also from the book, No Dogs Have Wings. What does it tell you? Does it tell you about some part of or some values of x, or all of them? All of them, right? So that is why you will use the universal quantifier. Okay, and then again you can use any variable for the values. You can assign it to a set. Okay, and then take this variable, sorry, like this. Okay, clear? Is it clear? Okay, next one is easy. It's you have the keyword directly over here, straightforward. Which quantifier will you use over here? What type of statement it is? Existential. So you will use this quantifier, and remaining solve it on your own. Okay, so we are done with the universal statements. Yes? we are done with universal statements, existential statements, truth and falsity of both types of statements, and how to translate universal and existential statements from their formal to informal form and informal to formal form. Next, we will look at universal conditional statements. This one is nothing, just that in the predicate part you will have conditional. Okay, you will have if and then. Other than that, because it's universal, so universal quantifier. Okay, this part remains the same. The predicate part, it will be in the form of this conditional. Okay, so if P of X All right. So in universal conditional statements, you know from the keywords universal, so universal quantifier, everything in the quantifier remains the same as your universal statements. In the predicate part, it is in the form of conditional statement, if P then Q, but you will write it as if P of X, then Q of X, or you can write it down like this. Okay, this will be your universal conditional statement. Here we have, let's look at it through an example. Here you have to rewrite this statement in its informal form. So first you should know how to read it. Can anybody try reading this statement? Anybody? Yeah, yes. For all values of X that belong to the set of real numbers, yeah, correct. Okay, so this is your universal conditional statement, and that is how you will write it in informal form. Okay, correct? Understand? Very straightforward. Okay, and yeah, in this example you just have to write it informally without the quantifier. So what information you need to have? You need to know what this quantifier is, what the domain is, and then simply how to read it. Okay, that is how you will simply write it in its English language form. Okay, and how to similarly how to transform or how to translate a universal conditional statement from its informal form to the formal form. If a real, let's look at first example. If a real number is an integer, then it is a rational number. So in universal conditional statements, always the quantifier will be this one, because it's universal. We are not looking at existential, so only universal conditional statements. Then you need to identify what is the subject. Okay, and here it's real numbers. For all real numbers, you can write it down in less formal form or in more formal form. This one is a bit less formal form, and the second one is more formal. So both of these are correct for all. And then real number X, I told you, you write it in its singular form. For all real number X, if X is an integer, then x is a rational number, simply like that. Or you can assign it a variable. You know that what will be the set of numbers, what will be the domain. It will be set of real numbers, and then you can, in the first part, which is the if or hypothesis part, if x is an element of, or if x belongs to set of positive integers, you can write down the symbol for that. Then x is set of x belongs to set of rational numbers. So for rational numbers, the symbol or notation is q. Okay, so both are fine. Okay, clear? Clear? Next are for you to solve. Okay, so we're done with the part 1 of quantified statements. Next we will look at negating universal statements, existential statements, and universal conditional statements. So let's look at how to negate universal statement first. I'll go through this one. Okay. All right, let's go through this information first. The negation, this is for universal statements, how to negate those. So the negation of a statement of the form this for all x in the Q of x is logically, so we'll look at the logical equivalences. Just like in last lecture, we looked at logical equivalences of the for negating the and or statements using De Morgan's laws, right? For and or statements, we had two De Morgan's laws, and there we had logical equivalences which help us in negating the statements. Similarly, here also we will look at the negation, logical equivalences. This universal statement is logically equivalent to existential statement where the predicate is negated. So what does it mean? Let's say you are given this universal statement and you have to negate it. What is the rule for that? You will change the quantifier. This is for universal. Please, no murmuring. Universal quantifier, in the negation, you will change it to existential quantifier. Everything else in the quantifier part will remain the same, and predicate will be negated. Simple. Okay. So what will you do in the negation of universal statement? Change the quantifier to existential, keep everything same, everything else same in the quantifier part, and negate the predicate. Okay. This will give you a negated universal statement. So for example, here we have a universal statement for all primes p. It shouldn't be like this. For all prime number p, p is odd. So what will be its existential quantifier? You change the quantifier to existential, a prime number p, a prime p, such that p is not odd. You could write even also, but it will restrict the numbers to only the set of even numbers, but which is actually not the case. That is why it's better to write not. Okay, so not odd or not whatever you have. Okay, so very simple. Quantifier changed to existential, and then you negated the predicate. This one. Clear? This is how you negate the universal statements. Is it clear? Next, we will look at how to negate existential statements. So, same rule. Predicate will be negated, and the quantifier will be changed to universal. Let's say this is the existential statement given to you and you have to negate it, you will change the quantifier to universal. Everything else remains the same in the quantifier part, and you negate the predicate. Okay? Clear? Okay. Okay, another example. There exists a triangle T such that the sum of the angles of T equals 200 degrees. So what will be its negation? You change the quantifier to universal. Okay, for all triangles T, the sum of the angles of T does not equal 200 degrees. So simple negation. Okay, clear? For universal conditional statements, it's a bit, it's related to your, the concepts. The concept is related to your previous lecture. Here what you will do is, in last lecture, if you go to the slides, slide number 20 and also 36, there I constructed a truth table for a logical equivalence as an example for you when we studied the logical equivalences. Oh. This one. Okay, 27. So here, this logical equivalence, this is pre-established. Okay, you can also verify it using the by drawing the truth table. So this is for conditional. Okay, so when you this is the logical equivalence of conditional statement. The conditional statement is logically equivalent to its disjunction where the hypothesis is negated. So you will take this, and you will, when you negate it, what you will get is something that we covered in here. We didn't go into the detail of how to derive it, but this is what we looked into, not in detail, but you should you should know that the negation of a conditional statement is logically equivalent to its conjunction, okay, where the conclusion is negated. So this information you need to know to negate universal conditional statement. So this is from where we will take it, and we will apply it in negating the negating the universal conditional statements. So if you look at the first part, negation of a universal conditional statement is logically equivalent to, the first part will be the same as when you negate the universal statement, it will be the same. So you will change the quantifier to from universal to existential, but in the predicate part you have two parts. You have if and then you have then. Okay, there you will use this concept of negating the conditional. Now this is what I am talking about, that you will take from your previous lecture. It is logically equivalent to the conjunction such that the conclusion is negated, and you will plug this or substitute this with this. Okay, so you will substitute 2 into 1, which will give you the negation of universal conditional statement is logically equivalent to, means this will be the negation, this will be the negation form of the universal conditional statement, existential statement. Okay, the quantifier will be changed such that P of x and negated Q of x. Okay, so the main thing that you need to know is that the negation of a conditional statement is logically equivalent to this. Okay, so in your universal conditional statement, I will write it down here. What will be the form? Negated form. let's say this universal conditional statement was given to you and you have to negate it. First part will be the same as the universal statement, change the quantifier from universal to existential, and in the predicate part write it as a conjunction where the conclusion is negated. Okay, so this will be the negation of universal conditional statement. And this is pre-established rule, the logical equivalence. You can verify it. You can verify this by drawing the truth table. Okay, and for that you should know, in logical equivalence we covered, we studied about a rule for these statements to be logically equivalent. We have one rule. You can construct the truth table and apply that rule and verify that these are actually logically equivalent to each other. So in your universal conditional statement, the predicate part will be in this form in its negation. Okay, clear? Understand? Yes? Yes? Any questions? No? Okay. Okay, we have one example, two examples over here for negating universal conditional statements. So here what you have to do is write a formal negation for statement A and informal negation for statement B. So both of them, I have given you the solutions. These all examples are from your book. Okay, so you can refer to the book for more examples also. Right, for all person P, if P is blonde, then P has blue eyes. What will be its negation? Change the quantifier to existential, keep everything else same, and keep in the predicate part, you will write it as a conjunction. The hypothesis will be remain the same, mean positive, such that, what is the hypothesis? If P is blonde, so it will be such that P is blonde, and this conjunction, you will have and over here, and then the conclusion will be negated. And P does not have blonde eyes. Okay, so this is how you will negate. This is the application. Okay, understand? Yes? Okay. Next one is in its informal form. If a computer program has more than 100,000 lines, then it contains a bug. So there is at least one computer program that has more than 100,000 lines. Your hypothesis is the same, positive. You have the conjunction part over here, and the conclusion is negated. Okay, and does not contain a bug. Okay, simple, straightforward. Understand? Clear? Which one? 32? This one? Okay. Okay. For today, we'll stop here. Okay. I'll mark your attendance. Please mark your attendance. If you are facing any issue in marking your attendance, come to me now.